Alright, welcome to FRQ number 2 for set number 7. So we're given this little diagram here. Cylinder on the top of a ramp. It rolls without slipping down the inclined plane. Alright, so part A, determine the translational speed of the cylinder when it reaches the bottom of the inclined plane. Okay? So if you can recall, we're going to find speed by using energy. So let's go ahead and set up energy. Okay, so we're going to have a KE linear and a KE rotational. I'm going to make sure you set that up correctly. Okay, so from here, it's just going to be a lot of expanding and simplifying. So let's go ahead and start doing that. This is 1.5. So M is big M in this case. Okay, and then you, for rotational, 1/2 pi squared. Okay. Okay. So the I coefficient for a solid cylinder or a disc is 1/2, and then m r squared. And then we're gonna go ahead, because it wants translational speed, we're gonna convert omega. So we know V equals R omega. So to get V, to get omega, excuse me, V over R equals omega. And you just have to remember that they are both squared. Okay. So R would cancel out. Oops. Alright, and then from there, you can cancel M. Okay. So now we're getting into some fractions. This is pretty simple. 1/2 plus 1/4. So 1/2 is equal to 2 over 4, 2/4. So then you get, so 2/4 plus 1/4, 3/4 V squared. And so we're looking for V squared. So remember, when you divide by a fraction, you multiply by the reciprocal. So you get 4GH over 3 equals V squared. And we're going to go ahead and square root that. And then since square root of 4 is 2, you can go ahead and pull that out. So, on to part B. Wants us to do a free body diagram. Okay. I like to draw a line when it's on an incline, just so I get a good understanding of where it's at. Okay, so our forces, pretty simple. there's gonna be Fn, FG, and that FG is going to have components. Okay, and then we also know, so this is on this side, so it's going that way. Since it is slipping, we know there's an F of K because that is what causes it to slip. So there is our free body diagram. On to part C. It wants us to derive an expression for the acceleration of the center of mass. Okay, so we're going to set up newtons. So we have Fgx minus Fk equals ma. Gotta remember big minus small. And f of gx expands to mg sine theta. Okay. Actually. Okay. So we can't necessarily just do, oh, like, f of gy equal to f of n, that kind of stuff for f of k for this time, because it is rotating, and f of k is what causes it to rotate. So instead, what we need to do is set up torque Okay, so F of K is our perpendicular force, and we already established I is 1/2 mr squared. Okay, and then omega. So we have A equals R omega. Okay, so to get A over R, you would just, or to get omega, you just get, or not omega, alpha, I'm sorry, alpha, you would divide A by R, and so that's how we get A over R here. Those would cancel out, and these would cancel out, so we get F of K is equal to 1/2 ma. You can go ahead and plug that in over here, so minus 1/2 ma is equal to ma. Be sure to write your variables constant. Like if you're gonna write a big M, make sure it's always a big M, or else you're gonna confuse yourself. And as a force of habit, I keep writing a small m, but that is a big M. Okay, so now looking at it, we can cancel out all the m's. Okay, so we're looking for A, so let's go ahead and move that over so we can get it by itself. So 1 plus 1/2 is 3/2. Okay, and so we're looking for A, so we're going to divide, and remember, when you divide by a fraction, you just multiply by the reciprocal, so that gets you 2g sine theta over 3 equals A. Okay, on to part D. Part D wants to know what percentage of the total initial energy is in the form of translational at the bottom of the ramp. Okay, so let's go ahead, set up our energy. And again, remember we have two types of KEs because the object is moving linearly as well as rotationally. So let's go ahead and solve for our total energy, or PE, because at the top it's just PE, which means that PE is equal to the total energy, so we're able to just solve for PE, and that's our total energy. Okay. Fractions again, so again, up here, 1/2 is equal to 2/4, so that'd be 2 plus 1 is 3/4. Okay, so PE is equal to that, which is PE is our total initial energy. So it wants to know what percentage is translational. Okay, so percentages, you want to have the part over the whole. Okay, so translational is linear, so that's 1/2 3/4 squared. Okay, those cancel out. And then, so now what we have is dividing fractions, which is multiplying by the reciprocal. Okay, and that reduces down to 2/3. And 2/3 is roughly 66.67%. So, translational energy is 66.6% of the total energy at the bottom. Or 66% of the total initial energy is linear at the bottom. There we go. Okay, moving on to part D, E, I need newspaper. Okay, on to part E. Let's see. So now it wants us to derive an expression for the minimum coefficient of friction between the cylinder and the inclined plane that required for the cylinder. Okay. So let's go ahead, set up. Okay, and so we're kind of emulating this, what we did for part C. So that's going to be FGX K equals MA. Alright, go ahead and expand. Okay, now, last time we went and we found variables for f of k, but now we can go ahead and break up f of k because we're finding mu. So that's fn. Okay. And we can use the a that we found. Okay. So keep expanding and simplifying. So Fn is equal to f of gy. So that means it's mg cosine theta. Okay. Actually, doing this, keep writing a small m instead of a big M. Okay. And this actually I want to combine. Okay. And that way we can go ahead, cancel out all the MGs. So now we're left with sine theta. Okay. Okay, so from here we're gonna do some moving around so we can isolate mu k. So first, to keep things like positive and not to confuse ourselves with signs, I'm gonna bring this over so I can combine it with this. So this is positive, so it's gonna be minus. So this is a 1 sine and this is a 2/3. So it gets us 1/3 sine theta. But then I want to make that positive, so I move that over. So that gets me mu k cosine theta. And that kind of just makes it easier, doesn't make things negative. Because if I would have subtracted this, you get negative, and then you have to divide a negative, and yeah, it gets you positive, but it's just easier, in my brain at least, to just do it this way. Okay, so we're left with this, and we want to solve for mu k, so we're just going to divide by cosine. So you get 1/3 sine over cosine is equal to tangent. So you get 1/3 tan theta is equal to mu k. Alright. Okay. So it tells us that mu k has decreased, and now the cylinder rotates and slips. It wants us to indicate whether the translational speed of the cylinder at the bottom of the incline is greater than, less than, equal to, as in part A. Okay, So if mu k decreases, translational speed is going to increase. So greater than. Okay. So now, so I ran out of storage again. So I'm gonna try to pick up where I left off and do my best to edit this clip to the first one. Okay, as I was saying, so it's gonna be greater than. So your FOK is going to decrease, and that means it's gonna be taking less away from the force that's causing you to accelerate, which means your acceleration is going to increase. And this is your translational A, meaning your translational V is going to increase, meaning it's going to be greater than because it's able to accelerate more. Okay. Part FII. Okay. So now it wants us to know if total kinetic energy is going to be greater than, less than, or equal to. Okay. It's going to be equal because looking at when we set up energy, you get P is equal to KE linear and KE rotational, right? Your height doesn't change, and everything else is the same except for your mu k. But your PE is equal to your KE. And if your PE doesn't change, that means your KE can't change. That means that can increase or decrease. So that's why it is going to remain equal. That just means different quantities are going to get distributed differently between KE linear and KE rotational. How much, like the percentages we calculated, that's going to change. Okay, on to part G quickly before I run out of storage again. Okay, the cylinder moves up on the other side of the ramp. Okay, so now it just wants us to draw another free body diagram, but now we're on this side. Draw, help me draw. Okay, so we're going this way, so that means we're gonna have an FOK this way, and FOG, and then our components. Alright, and that is our free body diagram, but now we're on the other side. Same thing, it's just your FOK is now pointing in a different direction because of the direction the cylinder is moving. And that concludes FRQ number 2.